Welcome back. In this lecture, we will address some issues related to flow field design. In an earlier lecture, we had given the components of a bipolar fuel cell. Flow field has to do with this particular component, and inherently, this component is also connected with the flow in the gas diffusion layer. Together, what we need to ensure is the flow field design and the flow in the gas diffusion layer should ensure uniform distribution of the oxidant and the fuel, but the trade-off is it should not have significant pressure drop. If the pressure drop is significant um, in the flow field that is being designed, that is not productive because this would decrease the efficiency of the fuel cell. So, with some balance, you have to ensure flow uniformity without enhancing pressure drop. So, there are variety of flow field design that has been first engineered and tried, and if in the last decade or so, computational fluid dynamics has also been utilized to um, analyze the different flow field that has been um, engineered. So typically, you make some the way the CFD works is that you try to measure the flow uniformity or the uniformity in the distribution of the reactants, and then try to engineer an alternate pathway. So if the design is involves a lot of circuits, typically the pressure drop is uh, quite significant, but it may enhance uniformity. So it's a matter of trade-off between uniformity and the pressure drop. Let's move on. These are fairly elementary fluid mechanics. So the central quantity we are interested in is in the Reynolds number. And the characteristic dimension can also be obtained from the area of the flow and the perimeter, relevant perimeter. From that, using Hagen-Poiseuille kind of equation, we can obtain the pressure drop relevant to the flow field. This should be you should be aware of this equation from your fluid mechanics classes. So this is more accurate in this region. It is not accurate in the entrance region. The length of the entrance region is related to the Reynolds number. So the flow field, this equation, the pressure drop in the flow field is more accurate in this region. Consequently, you can also calculate the pressure. The meaning of this equation should be fairly self-evident. That is delta P times the relevant area of cross section and the velocity along the z direction. So this would give you the volumetric flow rate, and this is the delta P. So if you know the pressure drop, you can also get the velocity in the z direction. Here, typically, this is the friction factor. This equation is utilized for obtaining the pressure drop once you know these parameters. This equation is used for obtaining velocity along um, the z-axis if you know the pressure drop. From all these things, you can obtain the volumetric flow rate in the channel. So this is the velocity along the z direction. This is the cross-sectional area. Substituting this, you get this formula. All these things are materials that are presented in the first course in fluid mechanics. So probably just refresh on how this equation is derived so that you understand the basis for these different formula that has been presented here. In the next brief lecture, we will address certain issues related to water and thermal management in a fuel cell. Thank you.